Is the microphone? Yeah, the microphone is working. Okay. Unfortunately, Joseph is not here. Yes. So, I've had a long association with Joseph, and I have some stories. So, as you can tell from this picture, much of the time that he and I have spent together is hiking. And almost every hike we ever went on had some unusual adventure happen. And this was actually the last one I went on a hike with him, and nothing happened, which is just as well. I have lots of stories about some of these hikes, and if I have time at the end, I'll tell you a Joseph story from one of these. But it's true, I owe him a great deal. You can read more or less everything I'm going to say. So when I was preparing for this conference, I had in mind something to do with Eisenstein series. And then during my early preparation, I came across a paper on the archive by Heiermann, Martino, and Opdam, which changed drastically what I was going to talk about for reasons which I hope I can explain. So the theory of Eisenstein series was, as it now exists, it was sort of begun by Selberg, but it really was created in its present form by Langlands around 1964 or 5. And nobody, and there's a book about it by Mugler and Valspagé, but actually, in spite of this book, nobody has really improved Langlands' arguments. And there's one part of Langlands' arguments which are notoriously difficult, and a handful of people, and not me is among that handful, a handful of people understand the argument that he's doing. And I'll try to explain later on exactly what the difficult part is. But until very recently, nobody has really tried hard to change Langlands' argument and make it simpler in some sense. And even, I would like to think, refine his results in Eisenstein series to get sort of what I call the fine structure of Eisenstein series. So this paper by Heiermann, Martino, and Opdam actually makes a first attempt, which is actually really remarkable. They not only explain how to get rid of the difficult part of Langlands' argument, and admittedly in the very easiest of cases, but they not only explain how to do this, but they also, at the same time, confirm a conjecture of Arthur's, which generalizes the Ramanujan conjecture. It's really a very beautiful idea. I've been talking to Eric here. I think that's the main thing I've been doing since I arrived. So I'll do that, and it turns out that what they do relates to some old conjectures of mine, going back to 1983, in fact, about how possibly to modify Langlands' arguments. So far, my suggestions are purely conjectures. So I'll begin by telling you basic facts about Eisenstein series, just for SL2 and GL2. Then I'll remark on what these three authors have done. And by looking, I say a few examples here, but actually I reduced it to one. And then I'll try to explain my conjectures. In the mini course I give next week, I'll say more about pretty much the same material. So I'll begin, actually, let me go back. So Joseph Bernstein has been responsible for many principles which most of us carry around in our heads. But one of the principles which I follow very often, which is not due to him, but it's due to Jacquet, is always begin your talk with SL2. And so it's usually a good idea. Not always, but usually a good idea. This is my notation. There's nothing unusual about the notation, so I'll just skip it. Except there's one slightly unusual thing. At the beginning, in order to understand what's going on, it's best if I don't assume that gamma equals SL2Z, which I will do eventually, just because it makes clear where the analysis separates from the number theory. And in this business, that's very important. What's weird about the theory of Eisenstein series is that it's all analysis right at the very heart of the matter. In the end, you're applying the results to number theory, but at the beginning, and all of Langlands' techniques are very, very difficult analysis. Good morning. Should I show? Joseph, I have something to show you. Okay. So if I have a smooth function on the arithmetic quotient by gamma, then I can expand it. It's invariant under gamma, so I can expand it in a Fourier series. And the first term, the constant term in this Fourier expansion is called the constant term. It's really a function of y. In general, it's a function of something on a Levy component. And under mild conditions, the important fact about this constant term is that under mild conditions on the function f, the difference between the function and its constant term is rapidly decreasing in a very smooth way. And if F is an automorphic form, something much stronger happens. Then, at least for GL2 or SL2, the difference is exponentially decreasing, but that's not an analytically significant fact as far as I can tell. The analytically significant fact is that it's just decreasing more rapidly than any polynomial, inverse polynomial in Y. And among the functions which you have on the upper half plane are the Eisenstein series. They're parameterized by a number S, which has something to do with the spectrum of the Laplacian. It converges only in a certain domain, which I'll picture in just a moment. It converges to a function which is an eigenfunction of the Laplacian with a certain eigenvalue. So from now on, I'll use lambda. I'm not going to write this again. It's a horrible expression to keep on writing. So I'll refer to lambda as it will always mean that expression. Well, it's meromorphic. It satisfies a functional equation, which means basically that the space of automorphic forms produced by E of S is just one. It has one dimension. Somehow there's a functional equation which makes things work out, right? The function E of S extends meromorphically, and its constant term can be written rather explicitly. So very explicitly, in fact, if gamma is equal to SL2Z, then you know it's a ratio of the Riemann-C function at S equals, at S and S plus 1. It's a very curious fact, actually, in some sense. So here's a picture of what's going on. Over on the right, you have the area where the Eisenstein series converges for the real part of S greater than 1. Huh? I'm very happy with that picture, actually. I debated putting various Israeli politicians on, but I thought I wanted to escape the lecture room alive, so I decided not to do that. Anyway, so we have a functional equation, and one of the important features of C is that its absolute value is 1 on the critical line. And the other feature which will play a role in this lecture is that if it has a pole at 0, and the pole has a value of, the residue has value 1, and what that means is if I take the residue of the Eisenstein series itself, then the constant term of its residue is a multiple of this, and that means that if S equals 1, which is what happens, then you just get constants. So the Eisenstein series have a simple pole, for SL2Z anyway, have a simple pole here, and the residue of the Eisenstein series are some multiple of the constant functions. The continuous spectrum is contributed by the Eisenstein series, and they all arise from the critical line here. Notice that the Eisenstein series themselves are just short of being square integrable there, so what you're looking at is a kind of an analog of analysis on the real line, actually. Now, the reason these monsters are over here is because, as far as I can see, it's a bad idea to ever think about wandering into this region. There was, it's Riemann's devil lurks in there somewhere. And, well, it's an interesting fact. So I was very happy. A number of years ago, Howard Garland started looking at Eisenstein series for Katz-Moody groups. And in his first version of Eisenstein series, he discovered what seemed to be the case, that his Eisenstein series continued up to this critical line and did not continue beyond that line. Since then, I haven't looked at what he's done since. I've heard he has some new version where everything extends smoothly and so on, but I think that's, in a sense, a factious thing. It's something you should try to ignore. You should never really depend too much on dealing correctly with continuous Eisenstein series over in this region.
Functional equation.
What?
What about functional equation?
I can't hear. That's
Functional equation.
yes. I don't know.
See, this is like you don't have functional equation.
I'm sorry. My ears are bad, and Joseph's accent is strong. So, no. Okay. Yeah, best avoided. These monsters are best avoided. All of them, I promise you. And I'll tell you later something about the construction. So basically, the construction first goes by series convergence here, and then you have to fiddle around to get into this gray region, and then you have to fiddle around to deal with some extra singularities. And that's pretty much the pattern of the construction of all of the Eisenstein series. So what good are the Eisenstein series? Well, the simplest statement just involves L2 of gamma of the arithmetic quotient, which I'll say something about in a minute. But actually, the real value of the Eisenstein series is that they can be used, you have to use Eisenstein series in the trace formula. So ultimately, the theory of, well, this is a controversial statement, maybe I'll still get shot. Ultimately, the whole theory of automorphic forms is about the Selberg trace formula. That's pretty much, that's my conception of the role of automorphic forms. Joseph he will shake his head occasionally during my talk. You can ignore this completely. No. And the trouble is that you have to deal with the Eisenstein series in the trace formula. There are so-called simple forms of the trace formula, but they don't actually get you down to what the long-range potential holds. But as I say, the simplest says, so the real statement about what good this is to tell you all about the trace formula, and of course I'm not going to do that. It suffices just now to tell you that the L2, the space of square integrable forms, is equal to a function of a sum of cusp forms, about which we know very, very little. And then we have the residues of ES. Remember, gamma is not necessarily SL2Z here. We may have some other residues in 0, 1, and we have a residue at 1. And then we have the continuous spectrum. And the continuous spectrum is isomorphic via some sort of Fourier transform to the space of functions on the imaginary axis satisfying this functional equation. If you want to understand where that comes from, well, you can get a partial explanation. If I take a function in CC infinity, I can define its Eisenstein transform by this, and then this satisfies this condition. So basically, the continuous part of the spectrum is filled out by the images of this map. Are there any questions? NR, do you have any questions?
No, not yet.
Okay. So I remind you now what the proof does. So the first proof, the proof goes in several steps, and the first step is to use convergence. So here's some sigma in what you might call the good region. This is the only region of convergence. There's a pole here, so they can't possibly extend. The second step, or the first step, I'm sorry, the 0th step really, is to show that the cusp forms are a summand. That's actually relatively elementary, although not trivial. And the second step decomposes the orthogonal complement of the cusp form. So the automorphic forms are cusp forms plus something which are not cusp forms, and that there are two parts, the Eisenstein series themselves, which come from the unitary axis, and the residues, whatever you pick up over here. And the proof of this, all proofs that I know of, and I can't imagine one that doesn't, they all involve a contour shift. So what you do is you start with an integral somewhere. In the usual proof, you start with an integral over you start with an integral, over this line, and then you move your contour to the left. And of course, that's a bit tricky because that means that when you construct the Eisenstein series, you have to know something about its behavior in the imaginary directions in order to justify that shift to the left. What you do know is, because the absolute value of C is 1, what you do know is that in the end, on this line, you get something which is square integrable. So what you're looking at basically is something about a limit of a distribution. So that's really the way to see the Eisenstein series, is they're distributions on the upper half plane. And what you're looking at are something like the physics theorem is all about distributions with Fourier transforms of functions with support on a wedge of some kind, a cone of some kind. That's really what's going on. It's hard to justify that in a precise way, but I think that's how to see what's going on. And of course, that shift, as I say, depends on how you construct the Eisenstein series, because you want to know the good behavior of the Eisenstein series in this region. And that good behavior is not immediately apparent from the way it's constructed. But all constructions do lead in some sense to good behavior. Okay. So what happens for GL2 instead of SL2 is just a modest extension. First of all, I can't use H anymore, so we're going to lose a little intuition. I call it a G mod K, and I identify the quotient with the positive diagonal matrices. And then the unramified characters of A are of this form, of course. And I have my co-root. That turns out to be very important in the long run in the theory. So I'll call this the exponent which occurs in the co-root, I'll call S alpha. And the reason is, well, that the AS converges for real of S alpha greater than 1. And the constant term is equal to this now, where W is the element of the Weil group that just switches the diagonal elements. There's a simple singularity now, not at a point, but along a whole curve where S alpha equals 1, and the residue is some multiple of the determinant. So just to fix the picture in my mind. So later on, you're going to see lots and lots and lots of pictures like this. And I have to tell you, I have been drawing pictures like this since 1983. I have never been able to explain them to anybody. So I decided to show you GL2 first in order to get you to see how to read these things. So first of all, the characters have dimension 4 in this case, including the complex dimension. So I can't possibly picture what's really going on. All I can do is picture the real part. So this is a picture of the real characters of GL2. And what we have is, so here, this line matches what I had before. So the picture for SL2 that I had before is just you have to extend this out for one dimension, one imaginary dimension. And so this becomes a two-dimensional picture, but now the residues all occur along this line. And what are the residues? Well, they're all multiples of the determinant to the power s. So s is a variable. S is the s1 plus s2, and it goes in that direction. s1 minus s2 goes in that direction. And so that gives me s. Okay? And the unitary representations all occur right exactly here. Okay. Okay, now I'm going to talk about SL3 in a minute, but for, I think, what must be perverse reasons, I'm going to tell you what the notation is for general use. So this is a sort of a preface of my talk next week. As I said, I'm going to look at a few, actually a few. Again, the word few here should be one, because I'm just going to look at SL3. But I'm going to give notation in general. It turns out it's just as efficient to do this as it is to explain what happens for SL3. So again, all the notation is standard. I don't see any non-standard notation. There's one thing which turns out to be very useful, which I hadn't quite appreciated when I began this talk. When you're dealing with split groups, it'll become apparent next week, I think, that how is a Chevrolet group defined? It's defined by a Chevrolet basis of the Lie algebra. That's the original starting point of Chevrolet's wonderful paper from '55. And that basis depends on looking at the canonical involution on the split group over an algebraically closed field. Now, what's really rather remarkable is that involution determines two things. It determines the Z structure because of the Chevrolet basis, and it determines K. So the groups K and gamma, there's a notion of compatibility between K and gamma, which I haven't seen emphasized, although everybody, Langlands certainly is aware of it. I've even had talks at me. But it's somehow something to keep in the back of your mind when you're talking about groups, that the K, the compact K and the arithmetic structure are somehow related. And this becomes actually rather an interesting question when you're looking at reduction theory, because then the difference between the two is somehow there's something to do with ramification and discriminants and something which I don't understand in the reduction theory. So it turns out to be, I think, a very subtle question. Anyway, in this case, because gamma G is split, the group gamma actually acts transitively on all of the parabolic, on the flag manifolds. And that turns out to be, that's not a serious fact, but it does simplify notation enormously. And the reason I do this is, in all my work on this analysis, I work with arithmetic groups rather than Adel groups, because the notation is much easier. But the one thing that the Adel groups have, which the arithmetic groups do not, is that the action is transitive on the flag manifolds. And I think that's the main simplification that occurs in dealing with Adel groups. Okay. I go on a little bit talking about notation. The unramified characters of any A, in fact, can be identified with Hams from the co-roots into C. That's pretty much standard notation. It's very important when dealing with Chevrolet groups because you're constantly using this. If you haven't made it explicit, notation becomes rather clumsy. I also assume that this is simply connected. That's just a mild technical convenience. And then that tells you what the characters, what the unramified characters of G itself are. So the unramified characters of G can be identified with the kernel of this map. You have to be very careful here because the toruses don't always split in a nice way. And of course, the nice thing about this assumption is that it holds also for the Levy factors. Any unramified character of M can be identified with a function on G, which is fixed by K on the right. And in particular, that's true of the modulus character. And now, in general, suppose P to be a rational parabolic group. And if I have a function on, well, the quotient there, then I can define an Eisenstein series. Many people call these pseudo-Eisenstein series, but again, that makes your terminology rather odd to distinguish. What's the difference between an Eisenstein series and a pseudo-Eisenstein series? And who is pseudo-Eisenstein anyway? Anyway, when defined, it's a function on gamma mod G, and yeah, and so the reason for the factor is just for compatibility in various measures. And its constant term is derived very simply as a function on, you go back to a function on this again. So your Eisenstein series starts with a function here, and it winds up with a function on the same space again. Okay, so we know what the constant terms are. This is very important to understand in Opdam's paper. We know exactly what the constant terms are for these Eisenstein series. They're given by sums of over the Weil group of various characters with arithmetic coefficients coming from the roots. And the constant term is just given by this. So we'll see later, I'll only show this for SL3, but we'll see some explicit examples in just a moment. So, Are there any questions now? No? Yeah, good.
Does that CWS have
I'm sorry, you have to yell.
Does that CWS have anything to do with intertwining operator, the normalization?
Yeah, it comes because you're calculating, it's exactly what it's the product of all the local factors in the intertwining operators. That's exactly right. So I'm assuming functions on G mod K, so that means, and what that translates to, when you translate this onto the Adele group, that means all these functions are fixed by the maximal compact, and you're calculating the intertwining operator on the K fixed vectors, both at the real and the finite primes. Okay. Yeah. Okay, so let's look at SL3. So we have the region of convergence is here. So here's again, I can't portray everything, the dimensions, it's 4 again. But here, so this is an analog for SL3 of what I showed for GL2. So here's the region of convergence. This is the real part characters. The region of convergence are the two-dimensional imaginary things sticking over here. And various properties of the construction of Eisenstein series allow you to continue that into this region. And then this is so the unitary spectrum now, the two-dimensional unitary spectrum is here. And now what's unusual here is it's a one-dimensional unitary spectrum that comes from this, which we're looking at representations induced from the parabolic subgroup. And this orange thing, well, it's where things go bad. I mean, in this case, so before, in the SL2 picture, we traversed over to the left and we wound up looking at poles contributed by zeros of the Riemann function. And that's what happens here, is you'll see in a moment, the form of the constant terms is such that as soon as you enter this region here or go anywhere outside the gray region, you find yourself trying to swallow Riemann zeta zeros. And that's a bad idea. It's a very bad idea. We'll see that that explains in a good sense all the difficulties that Langlands had with his construction of Eisenstein series. I don't know that Langlands ever mentions that as a problem, but it's clear he knew about it. He does not always write so clearly. We have, the point is that we do have some singularities, and they're sort of easily controlled singularities. So we have, in this region, this is convergence, but there's a pole here, it's a point residue, and the point residue of Eisenstein series contribute constants to the function, and in fact, Langlands has a very famous work where he explains how the residue, the point residue here, and the theory of Eisenstein series allow you to deduce the volume of the arithmetic quotient, which leads to the Tamagawa conjecture, the Bayes-Tamagawa number conjecture. And it's a rather subtle paper of Langlands, actually. But anyway, this is a point residue, but you also have line residues. So everywhere along here, your Eisenstein series will have residues. And so above each point here is the residue of something. So again, over this point, you have a one-dimensional imaginary axis sticking out. And over here, you have a one-dimensional residue, which is unitary. So this point and this point contribute to the unitary spectrum of the arithmetic quotient, but because of there's a functional equation for different elements of the Weil group, and this point contribute the same part of the one-dimensional. Actually, they contribute the same one-dimensional spectrum. And Langlands' argument, in this case, Langlands' proof of what the spectrum is, well, he started out here. He starts out with some sort of an integral over here, and then he has to move his integral. He wants to calculate the inner product or something. And as opposed to in the SL2 case, you just move a line across, but in this case, you have a rather complicated residue problem. You start here, you move some contour in here until you get to here, which is the spectrum you want to get to. But in the process, you cross lines here, so you start here, you come here, then you move along here because you have another, then you move along there. It's a very complicated process. And as I say, part of the process is simple, and part of the process is very complicated, but as I say, Opdam and his colleagues have managed to hint at what might happen in the long run to simplify a good deal of Langlands' arguments in the contour motion. Okay. So here's a picture again. I think in terms of pictures always, I'm afraid. So this just tells you what the coefficients of the constant terms are. So the constant term of the Eisenstein series is one term for each one element in the Weil group. There's 6 altogether here. And so these are the coefficients, and of course they're just given by this. As I said, it's a product. Each one is a product over various roots, and these are the coefficients which occur. And of course you get into trouble because, remember, so here's the line where SA equals 0, and here's C of SA. So as soon as you go from here to here, you're meeting the zeros of the Riemann function. So outside of this gray region here, the Eisenstein series for SL3 behave badly. Absolutely, no question about it. It's conceivable if the Riemann hypothesis holds, then you could deduce some interesting thing, but until we know that, you pretty much suck. It would be horrible if Langlands functoriality conjectures depended somehow on the Riemann hypothesis. That would be your worst nightmare in a sense. Or conversely, if the Riemann hypothesis, never mind, no. You'll be amused to know, so just a couple of days ago I got email from Jim Arthur. He has made a bet with Harder that Jim bets that functoriality will be proven before Riemann, and Harder bets that Riemann will be proven before functoriality. But it's a very small bet, only 100 euros. So we shall see what happens. Of course, what's most likely is that all of us will die before either one of these is completely done. In which case, the bet is defunct. It doesn't go on to their heirs. Okay. Okay, is this picture clear? Because I'm going to move on to more pictures. So, okay. So what's new for SL3, as I said, is that there's a one-dimensional piece of the spectrum. So now in this case, L2 is the sum of three parts: the constants, the functions on the two-dimensional unitary spectrum, satisfying a functional equation, which you can see here. And then there's a one-dimensional spectrum. M here is the GL, it's the parabolic with GL2 up in the upper left-hand corner. And that contributes to this. These are the unified, so this is a one-dimensional space of unified unitary characters. The point is that both the two parabolics which I get both contribute the same one-dimensional part because of the functional equation. And that's essentially because the two Levy components are conjugate. So whenever you have two parabolics with conjugate Levy components, they're said to be associate, and they always contribute the same part to the spectrum. It's just part of the functional equation. Okay, so now this is a picture of Langlands contour motion. This is my picture which I showed in 1983, which nobody has understood since. In those days, we didn't have computer graphics, so I had to draw it by hand. So I had transparencies, which were a little more cryptic than this, but not a lot more. I'm not going to say much about this picture except to say that sort of you see different phenomena occurring. So you start by integrate over this two-dimensional contour, and then you move it in, picking up a one-dimensional residue, another one-dimensional residue, another one. So what happens is you keep sliding all these things. In the end, you get to your functional equation. It's a little mysterious what happens. In the end, so for example, for the two-dimensional spectrum, it's fine. You just get a two-dimensional integral here. For the point residue, it's fine. You just get a point here. But for the three-dimensional one, you get three different, in the end, you get a sum of three terms, here, here, and here. And that's basically because the constant term, as I'll show in a moment, that's because the constant term of the residue has three different components. And also because there's a functional equation. So Langlands goes to a great deal of trouble. The hardest part of Langlands is explaining somehow the relation between the different parts you get which correspond to the same part of the spectrum. Opdam and his colleagues, again, have an explanation of that, which is very nice. Or a partial explanation, at least. I haven't read the whole thing. Are there any questions? When I give you a quiz at the end, it will be about this picture, so you should look at it carefully. Ari, do you have any questions? Okay. Hello?
You might remark that when you go from the dark gray, region, crossing one of the vertical walls, or whatever, where you have a...
I will mention, before you give away the trick, I will mention that in just a moment. You're a spoiler. God forbid any friend of mine should be a spoiler. I'll save you from yourself. Okay. Right. I can't remember what I was going to say that next. Here we go. Yes. Okay, now. So, yeah, so as he says, I forgot something. Thank you for reminding me. So what happens here is very interesting. So basically, I thought of putting up a picture of this, but I thought just to try to explain it. So basically, when we construct Eisenstein series, they're basically, unfortunately, two different kinds in a way, a very rough categorization of the construction of Eisenstein series. One is from Cuss forms, and one is from these other things which somehow arise from discrete summands on other parabolics. Now, the Cuss forms, the behavior of the Eisenstein series for Cuss forms is relatively simple because the constant terms have a very simple structure, extremely simple actually, by definition. And the other ones are kind of messy, but basically the principle, I don't know if our Langlands ever formulated this, and he never dealt with it directly, certainly. Basically, the principle is that the two kinds of Eisenstein series shouldn't look any different. In other words, the picture, when I induce the constants from a parabolic to G, the picture that I get should look exactly like the picture I had for SL2 or GL2. There should be no really dramatic behavior caused by all these zeros coming from Riemann. So what happens, now you see that here, and there's some sort of problem in that, because when I cross this line here, I pick up a residue of which it becomes a one-dimensional integral. Now this one-dimensional integral is floating there for a little while, but then after a while you have to start moving it down because you want to get to the unitary spectrum, which is here. So you move this contour down, and when you do that, you cross this. When you do that, you pick up the constants. And you keep moving it down, moving it down, moving it down, and now something terrible happens because you have to cross this line to get to the unitary spectrum. This is the basic difficulty that Langlands' theory of Eisenstein series faces, is that he knows immediately that he has to deal somehow with the potential zeros coming from the Riemann zeta function. And that's the whole point of the most complicated part of his argument, is that he has to deal with that problem. So this is the picture. If you look at this line here, this is basically the real part of the line for SL2 that I showed before, only it's not because it's coming from constants. But you should see that. I mean, I could have pictured this. That's what I debated drawing another picture for. It's unnecessary. It's the same as the picture for SL2. We have a pole residue here. We have the unitary spectrum here, and I want to move from here to here. But we have to deal somehow with what terrible behavior can happen there. Okay. Any questions? No? Okay. So here's a little bit more. Unfortunately, what's different from SL2 is that the constant term of the residual Eisenstein series is not quite as simple as it is for SL2. It can't be, but so in the case of SL2, there were two constant terms. In this case, there are three because we're looking at cosets of a Weil group. So here's where the residue happens, and here's where the contour motion of Langlands happens. When we take the residue of so the constant term of the residue is the residue of the constant term. So when we take the residue, the constant term of the residue, we get a sum of three components. So if my S is here, and I take the residue at that point, then a constant term has three sums, here, here, and here. And these are the coefficients which occur. Here's 1. Actually, it's not 1. It's 1 over C of 2. There's some constant which occurs in all of these coming from the SL2 residue. And there's this is this, and this is this. Now, what you can see here, we're in this region here where S beta is less than 0. And that means that potentially we have poles. So this term is fine. There's no problem. This behavior of this function is very good. But the behavior of this function looks like it might be very bad because we have this factor here. So as soon as S beta goes from 0 to minus 1/2, this causes some potential trouble. And this is exactly what Opdam and his friends deal with. So because, and again, I noticed this in 1983, but I didn't know quite how to do it. I made a conjecture and I did some computations. This sort of thing actually happens all the time. But let me explain what it is that happens. So we have these constant terms, and we have potential trouble. But in fact, when you expand the constant terms, you get this wonderful fact that the denominator here is wiped out by the numerator here. And so we don't have to worry. It's precisely this term that causes the trouble. And because of this cancellation, we don't have to worry about it. Now, there's an interesting fact, which is that when Langlands calculates Tamagawa numbers, he uses implicitly a result of constants, which also involves a huge cancellation. And this is basically the same kind of phenomenon. I noticed this a long time ago, but I didn't have a proof that was very good. But recently, again, this is one of the two major results in Opdam and company, that they actually explain that this cancellation occurs for all split groups. So that you never, at least for the unramified principal series, when you're moving the contours in Langlands' argument, you never, in fact, have trouble moving the contours across because of this marvelous algebraic cancellation. Miraculous, I would say. Okay, so it turns out this is an extremely general phenomenon. In 1983, when I started this, I don't think I'll explain why, but I did start this a long time ago. I was fascinated by this. First of all, I noticed only recently, for some reason I didn't look at Langlands very carefully, but Langlands has two examples he does in his papers, one for SL3 and one for G2. And in his tables, it's clear that he knew about the cancellation. His tables do not have the extra factors. He just throws in something. And so he was quite apparent. I asked him recently in email if he had sort of thought about the cancellation taking place, and the answer is he's forgotten. I think he just doesn't remember what he did. Langlands, if you know Langlands, then you know that his brain works in amazing ways, so it's quite possible that inside his head somewhere the cancellation took place and never made it to his outer consciousness. He somehow he's capable, was when he was younger anyway, capable of enormous calculations, like some other mathematicians I know, capable of enormous calculations inside the brain without actually making them conscious. That's one of the gifts that he has, which makes it hard for us to read his papers, although a little easier for him to write them. So I verified it in 1983. I can't remember whether it was 83 or probably a little bit later because my first computer I acquired in 84. And I was going from New York to Montreal to a conference, and I had my new laptop. In those days, HP had a laptop which weighed 1 million pounds and ran out of juice. It had a lifetime of about, I don't know, 20 minutes. And so anyway, but I did. Running on the train north from New York to Montreal, I wrote my first Weil group program just precisely in order to check that this conjecture worked for some groups of higher rank. And I was very pleased. I verified it all the way up to F4 in a certain number of cases, actually. Yeah, Turbo Pascal. Probably I'm the only one in this room who has ever programmed in Turbo Pascal. Very good, very good. I taught Pascal for many years. It's a wonderful language. Superseded, yes, but not entirely. The thing was, about Turbo Pascal, you have to understand. So I can't resist this nostalgia. My HP laptop had 256 kilobytes of total memory. Of those 256 kilobytes, you got to partition it into a hard disk and your active memory. If during your program you got a little confused, the program would wipe out. In writing to the memory, the program would wipe out your active memory, in which case you would have to reboot the machine all over again, correct your error, and start again. Incredibly painful process. But Turbo Pascal ran inside that 120. How many programs today will run inside 128 kilobytes? Turbo Pascal would do this with room to spare. It was just a marvelous program. Okay. So, okay. Anyway, one of the two theorems which I like of H, DM, and O is that they verify this cancellation from ramified principal series. A very nice argument about root systems, actually. And this allows, in this case, for the ramified principal series, a drastic simplification of Langlands arguments. Namely, it just makes the contour motion trivial. You use estimates on the growth in the imaginary direction of the Z function, and it works out beautifully. So now, let's see, let me go on one step. Let me go back again. Yes, okay. So it says, now, another way of looking at it, however, is, yes, that's it. So this says that the constant terms of the ramified principal series is well behaved. What about the residue itself? Well, there are various ways to do this. In general, the relation between an Eisenstein series and its constant term is intimate. One is more or less like the other as far as analytical behavior is concerned. There are some modest modifications of that, but that's the basic idea. And in this case, it works well. Yeah, don't pay much attention to the second paragraph. But here's the point. So there's a relatively simple construction of Eisenstein series for SL2, depending on some analytic arguments on Hilbert's, well, there are different ones, but the one I like is depending on Hilbert space arguments for unbounded operators, the Laplacian, in fact, or the Casimir operator in other cases. Now, this argument is very nice, and in the form of the argument, which I like best, you immediately do some very strong analytic properties of the Eisenstein series. Now, it's sort of curious that this then tells you something about the Z function, but of course not very much, because the constant term of the Eisenstein series is a ratio of Z functions. So actually you obtain very weak information, but it's more than you know about. And Langlands used this in general for higher rank Eisenstein series to deduce, it at least tells you that the Z function is meromorphic continuation, even though it doesn't tell you very much about numerator or denominator. And it's compatible with a functional equation, but doesn't give you a functional equation. Now, in general, you might ask, well, what if I'm looking at Eisenstein series which don't come from unramified principal series? Well, in that case, you're looking, of course, at Langlands' entirely new category of automorphic L functions. And so what you'd like to do, again, is deduce properties of automorphic L functions from properties of Eisenstein series, and that's, of course, what Langlands does, but he obtains rather weak information. But this argument of Opdam and company, it doesn't work, as far as we know, it doesn't work yet anyway, in general, when you're constructing even from cusp forms. And so you'd like to know somehow if you can apply analytic behavior of the kind, if you get something like the cancellation for arbitrary Eisenstein series. Now, I'm sure that you do, actually. That's because I have a conjecture which is plausible, not at all trivial, and I don't know whether it's true or false, really, but I verified it in many hundreds of cases, actually. So which I want to explain to you next. So what's true is that the cancellation behavior of Opdam and his friends is related very strongly to the allowability of a method of constructing Eisenstein series for SL2, which is originally due to Colin de Verrières in its nicest form. So this would lead also to a strengthening, which I will not talk about today, a sort of a different version of Eisenstein's, of Langlands' harmonic analysis on arithmetic quotients for a kind of Paley-Wiener theorem. Okay, so I'm next going to tell you Colin de Verrières' construction. Are there any questions? I think I'm just perfect for time, actually. No questions at all. I must be making a mistake. No. Joseph, you have no questions? Okay. Huh? Okay. Okay. So let's look at what happens for SL2. So the key fact about geometric arithmetic quotients is that you can partition the arithmetic quotient into domains parameterized by rational parabolic subgroups. So in the case of SL2, this is particularly simple. I look at all the different cusps I have, and to each cusp, I get a region, which is very nice. And what is very nice means, so here's what happens for the cusp at infinity. I can partition the fundamental domain into two pieces. One of them is just little teeny-weeny region down here, which is compact. And up here, I have a region which has the property, this is HY. So HY is the open region above Y, level Y. And what happens is that this region is actually a very simple region. It's not just gamma. I mean, H modulo gamma is a very complicated space, but HY modulo gamma intersect P is very simple. It's just a cylinder. And the point is that this natural canonical embedding, canonical projection is actually, or injection is actually an embedding of this and this. So the whole basis of analysis on arithmetic quotients is that you have this partition, and the whole point of Eisenstein series is to relate analysis on the whole quotient in terms of analysis on these different pieces. That's not actually true, but it's very close. It's ideally true, and it's something that you have to think about when you're doing the work. And this is a general phenomenon about arbitrary arithmetic groups. So again, we have a constant term, which I remind you of what it is here. Now, we have what I call a partial truncation. So we have a truncation operator. So it just takes the constant term. So instead, I take the constant term, and on this region, which is the parabolic domain, I call it, we look at just the constant term alone. That's a function on this region, which is invariant under horizontal translations. And so now, to define a truncation operator, parameterized by Y, first of all, I look at the constant term and I truncate it. In other words, I truncate it below the level Y. And then I take my truncation of my function f on the quotient, and I just subtract off this constant term made invariant. So all I'm doing really is taking this constant term, making it invariant, and then subtracting it off from f. And this makes it work because of this property. So this property about here sort of guarantees, if I look at translates of this region by different elements of group, I get all these disjoint circles that you've seen in different kind of thing. Again, I might have pictured that. And the point is that those circles are all disjoint, and what that means is that the sum that we have on the next page is a locally finite sum. Again, this is a phenomenon for arbitrary arithmetic groups. On mild conditions on F, as I said before, the truncation is rapidly decreasing, and that's the key fact. And the other key fact is that my original function f is a sum of these two pieces by definition. What's not by definition, but it's easy to prove, that this truncation is orthogonal. This expression, the sum is orthogonal in a very strong sense. My L2 norm of f is equal to the L2 norm of the truncated part on the full quotient, plus the part I'm truncating on the nice parabolic domain on this space. And that's actually, again, the basis of analysis, in some sense, of all of Jamartha's analysis on arithmetic quotients. I remind you of this picture. I got tired of drawing more dragons. I have a whole file of dragon pictures, but I got tired of putting them in. So whatever dragon you like, you can put down there. And now, how does the construction work? Well, the Colin de Verrières' construction, first of all, we have this region of convergence where there's no problem. And then it turns out that his argument extends this into this gray region. And then there's some third part. So it's three steps: convergence, extension into the gray region, then extension everywhere else. And the everywhere else includes, which the first part of the argument does not, includes this region here. Why special about this? Well, for these values of S, my value of lambda of S, the eigenvalue, is negative. Now, we know that the Laplacian acting on just the space is automatically a negative operator. which means that the spectrum is contained in the negative region between minus infinity and 0. And so what's true about this gray region is that that's the resolvent set, corresponding to the resolvent set of the Laplacian. So Calandra-Verdi's argument is going to use the resolvent of the Laplacian on, for values of S where lambda S is not in the spectrum. I don't know, and that's Langlands, well, it's Selberg was the first person to discover such an argument. There's a long history of how that came about. But what I didn't realize until recently, I still have to investigate a little bit of the history. I attribute this part of the argument into the gray region to Calandra-Verdier, but actually I'm pretty sure that Walter Rilke, a student of Maas, was the first person to use that. Rilke, unfortunately, could not extend it further into the red spectrum. That was Selberg's contribution. Okay. So the constant term is this. Here's Calandra-Verdier's argument. The constant term is this. The point is that the second term here for a real part of S greater than 1 is square integrable. So we think of it this way. The constant term of ES has two components. One of the components is one that we understand completely. It's a very simple function. The other part we don't understand completely at all, but it's square integrable. That's the key fact. So what we do is, in order to construct it, so we now have this definition that works for real part of S greater than 1. We want to extend it to other values of S. So we do is we take a smooth function on 0 infinity that, remember my y value is something where the level which is high. And I take my this vanishes for this, so you get a little function which looks like this. And then I define a function E of S1 to be E of PG times this. So this is kind of like what I did before for truncation, except this is a smooth function. I define a function f of s equals delta minus lambda s times this. Now, because of the way I do this, this has compact support in the band between y and y plus 1. So the graph of this might be a little something like this. So I look at, in the region again, still for real part less greater than 1, I look at ES minus that smooth truncation, and this is now square integrable. For real, and now that means that I can define sort of the missing part of the Eisenstein series by this way. Because I have this, because this is equal to 0, I have this equation between S of 0 and S1, and that means that I can define my Eisenstein series itself as being the resolvent of the operator with the sign for trivial reasons applied to f of s, which is square integrable. Furthermore, what's really nice in the further analysis is it's very easy to give a good estimate of my function f of s as a function of s, and you can show that it grows maybe as the imagined real part of s goes to 0, but not too much. And so this allows us first to define E of 0s and then also E of s as long as lambda does not lie on the spectrum, what I called the potential spectrum before. So as I say, you apply estimates here. There's a spectral theorem that gives a very good bound on this, and this is another way of justifying contours in Langlands' argument. What's really nice about this is that it works whenever you're inducing from a maximal proper parabolic, you're inducing a cusp form. Exactly the same argument works, slightly nastier for technical reasons, but basically almost exactly the same. This was first put in print by Werner Müller in his big Annals paper, and works like a charm. So there's some things to think about, though. So what this is saying, if you look at this argument very carefully, I'm actually fascinated by the argument. I wish I understood it better. It's a very simple argument using unbounded operators. It says that the Eisenstein series are the solution to a boundary value problem. What kind of a boundary value problem? Well, I wish I knew. So when I first started working on Eisenstein series, I thought of this immediately. I was very optimistic. I thought, I've seen this argument before. If you teach engineers about the heat equation, you show them, although you never tell them this is what you show them, you show them that log R is a fundamental solution to the heat to the Laplacian, and you do this by taking a tiny sphere, a little circle around the origin, and then making that shrink and using Green's theorem in between, and in the end you get, wow, voila. Now, I would like to think of this in a similar way. I think what's going on, there's some kind of boundary on which you have these L2 functions, or not L2 functions, something like that. I have no idea how to make this work, but I think that's what's going on. And to tell you the truth, I think this is a fantastic idea if anybody could make any sense out of it, because I think it explains almost all of Arthur's asymptotic estimates that occur in the trace formula. There's something going on at a boundary in infinity we don't even have a clue about. all of Arthur's arguments are something like Arthur's arguments often mirror exactly this epsilon goes to 0 business. You take some limit and you get something wonderful happens, and voila, but nobody that I know has any idea as to how to make this work.
This epsilon is the same as y before?
It's the same?
You had y before, the cutoff, is it the same as 1 over epsilon, or what do you mean here?
I don't have any, there's nothing y.
So where is
Oh, y, you mean epsilon, yes. Y is epsilon, you go off to infinity somehow. Yes, so actually now I am going to explain, I still have time, I think I have 10 minutes. I will explain, I hope. So I conjecture that the same idea that I just explained to you, Collet-Verdier's argument, can be applied not just to Eisenstein series associated from quest forms, but to arbitrary Eisenstein series associated to discrete series automorphic forms on quotients. So in order to do that, let me summarize what the argument is. First of all, you start with the region of convergence for the Eisenstein series. A major part, you look at its constant term, go ahead, look at it. And you find a component of you examine it carefully, actually, let's put it that way. You find a component of the constant term that's well defined, or many components. I can see a typographic here. So you have the constant term for this Eisenstein series comes in 2 parts. There's a good part, which is everything is well defined. That was y of s something something. And then, if you're lucky, what's left over is square integrable. And so your hope is that somehow you can subtract the stuff which is nice, and somehow use that part which you've cut off. You apply some sort of differential operator. Actually, what I have in mind is an ideal of operators to that good stuff, and get something which is of complex, or an L2, and you apply some kind of resolvent to that to construct the Eisenstein series in general. But in order to make that work, and this is part of the title of my talk, in order to make this work, we have to understand the truncation. So the key process for SL2 was that you have these properties, the truncation operator. You know what it does, and you know that if I subtract off the truncation, the constant term, you get something rapidly decreasing. Those are the 2 properties. And luckily, Arthur has indeed defined, following some suggestions of Langlands, Jim Arthur has defined a truncation operator on arbitrary arithmetic quotients.
For SL3,
Hello.
for SL3, can you do it for SL3?
I'm about to do it for SL3. Sort of. Yeah, of course you can. Oh, you mean, yes, so I can do it in some cases. You mean can I prove my conjecture for SL3? I can do it, yes. There is, however, one part missing. So I can do the truncation. There is one technical feature missing in all groups. There's one that I will tell you. So at one point, I'm applying the resolvent operator to this function f of s. In order to make everything work that I need to know some estimates on the growth of f of s as a function of s. And this I do not know how to do. It's a question of geometry. As you'll see, the truncation operator is a little bit complicated. And so I'm dealing with a very, I don't know what it is. It's some sort of boundary value of distributions question, which I don't know how to answer. Even for SL3, I don't know. My intuition somehow fails, and I'm sure it can be done. It's my fault, not the problem is not that hard, I think. But the answer is no. I cannot do everything I want, even in the case of SL3. Okay, so as I say, the key fact in higher rank is that we have this partition. I can do that. I say this is the most fundamental fact about geometry on this. Oddly enough, I don't think anybody noticed this before Jim, although again, Langlands had some suggestions of this. And associated to this partition, we have some truncation operators as well. Now, these truncation operators are very puzzling. Everybody who uses in automorphic forms who refers to these truncation operators, first of all, they always refer back to the original source. I don't think anybody has reproven any of Arthur's original statements. His proofs, on the other hand, are a little abrupt, and in a few places actually misleading, as Lebesgue pointed out to me once. These are redone actually in one place. In the recent book by Volkswagen and Lebesgue, they redo all of Arthur's arguments, which is not bad. It's a very good exposition, actually. That's the only other source. So I will summarize the properties of Arthur's truncation. I'll do it very quickly. I don't have time to do this part. I'll just tell you, I'll give you a little tantalizing hint. The Arthur's truncation is really an elaboration of a truncation on Euclidean space. So if I have a convex body, I can always refer to exteriors of different faces. And there's a basic theorem in truncation theory on Euclidean space to Rubio and Verne, much later than Jim, actually. They had no clue that Arthur had actually worked on similar things before. So there's a result about convex functions in general in Euclidean space. And Arthur's truncation theory mirrors that Euclidean truncation space, Euclidean truncation, but of course he didn't know it. And associated also to the truncation operator is a partition of the Euclidean space into domains parametrized by the faces of a convex body. And again, that's exactly what Arthur's truncation theory gives you in automorphic quotients. Arthur's truncation is in effect something about the rational building of an arithmetic quotient, which I don't have time to explain. So he associates a truncation operator to each rational parabolic, and this has two properties. First of all, what I call strong orthogonality, which is that I can take my f and I can write it as a sum of pieces, and the L2 norm of f is the sum of the L2 pieces on the different components at the boundary, so to speak. And second of all, it's decrease if f has uniform moderate growth, and this is rapid decrease. So now let's look again at what happens for SL3. Here's the residual Eisenstein series. Here are its constant terms. Here's the potentially bad behavior because of this cancellation. But now the wonderful fact is that this little piece here, and in fact this whole ray, is all contained in the region where the constant term is L2. So that's the basic fact. And furthermore, that's true of all the things. So you can read off from this exactly. I think I have to stand up, unfortunately. So I will now have to try to explain what happened. So first of all, this picture shows you the constant term for the minimal parabolic. But if you tilt your head sideways, you can also see the constant terms for the other parabolics. So for example, the constant term for one of the parabolics is given by this. So you have this pieces spreading out like this. So, and all those are L2. They're all L2. It's a wonderful fact. So yes, indeed, in this case, it's some potential for applying Colin de Verde's technique. Now, this is exactly what happens in a large number of cases for other groups. I'm actually, as I speak almost, I'm writing a program that will verify this for more. There's a little bit of complicated work to be done. But it's certainly, I've never seen any failure, although I'm not sure if it always holds. I'm pretty sure that the conjecture in general holds. So the conjecture is you can always subtract something good to get something in L2. What I conjecture very strongly is that this little red, so the little red part is where things may go wrong. I conjecture certainly that that's always an L2. Whether that, it's also true that the whole fundamental domain, so to speak, I'm not so sure about that. My memory tells me that one of my earlier programs found a counterexample to that, but I'm not sure. Anyway, it's at least plausible that Colin de Verde's techniques ought to work to construct Eisenstein series. Now, the most interesting part of what I've been working with is that this works for constructing Eisenstein series coming from proper maximal parabolic subgroups. That's because you have, well, if you're working on the upper half plane, you have Laplacian, or in general you're working with a Casimir operator, and that turns out to be sufficient in all cases. But suppose you want to construct Eisenstein series coming from other parabolic subgroups. Then you have to think about, it's not just the Casimir operator anymore that you're looking at. You're looking at the entire spectrum of dk invariant things. And so you're wondering what kind of a spectral theory for unbounded rings is. And the answer is nobody has any clue. There is no, I'm amazed actually. The more I look at this, the more amazed I am. You'd think that some crazy physicist somewhere would have, because the question occurs in quantum mechanics all the time. All the time you're looking at observables that you commute with each other, and so of course you'd like to know something about a spectrum. There is a theory for bounded operators, and this theory is actually extremely elaborate and very beautiful, mostly due to Gelfand, I think. So that works well, but for unbounded operators, there's no hint of this. Now, I myself had a weak idea that it had something to do with X. So what you're looking at this ring, and what replaces the resolvent is some Cazul complex. So the resolvent is, philosophically speaking, the resolvent is a homotopy operator on a Cazul complex. And this notion was made more precise by a mathematician at the University of Utah, unfortunately died in painful circumstances. Of old age, however, I have to say. He didn't die too young. But he had a very nice idea. And there's a number of interesting papers by Joseph Taylor on, I forget what they're called, commuting operators and spectral theory, something like that. They don't actually tell you what to do for unbounded operators. And even in simplest cases, it's not clear what the correct theory is. But I'm pretty sure that in the long run, some genius will come up with a replacement using Cazul complexes and homotopy operators to construct all Eisenstein series in one blow. I'm through. Whew. So I would like to add one point before any question. So I wish to point out that the advantage of giving a talk by slides is you control the timing. Your timing of your lecture is not controlled by how fast you can write. It's controlled by how fast you can push the button. It's a tremendous virtue in giving a talk. I finished exactly on time. Not just sheer chance, but because I had some internal mechanism that told me when to keep on clicking. I wish more people would give intelligent talks by slides. Thank you. Go ahead, Anthony. Yes, Nadja.
Could you please elaborate about how which works of Frank imply?
I'm sorry, I can't hear you.
Can you please elaborate which works of Jens Franke implies the result that you mentioned?
Yeah, he has the result that you could multiply the Eisenstein series by some polynomial with real coefficients to make things work. If you realize that and you combine that with what you know about the zeros, and something nice has to happen. I haven't read Franke's paper. It's an isolated paper many years after his original incredible work, actually. So I didn't pay too much attention to it. I knew that somehow somebody would come along with an argument like the one that Opdam and company came up with. That's a much better argument.
Does he explain the cancellation? Are those cancellations somehow explained follow from his work? The cancellation between the...
No. You have to combine what Franke tells you. Franke tells you multiply by a polynomial and everything's nice. That's what I'm not quite sure how he does that. I just haven't read it. I have great difficulty reading Jens Franke's papers.
So the photographer's waiting downstairs, so we'll thank you.
Okay.